Oh, it's got the wrong. Don't you love technology? I got to go through the process of reconnecting it. This is just the way things are. All right, now let's go here. All right, looks like this is going to work now. Okay, that worked. Test, test, test. Okay, that worked. All right. Close that. So we are recording, I believe. So in case you missed class, yes, I am recording. Okay, so Jupyter Notebook is down. We're going to talk about ACM. And this is why we want to learn about gates and things, is that on this, what we have is this article that I'm bringing up now, just remembering to do this, is what they've done is they've used some mathematical tricks to encapsulate floating point that reduces the energy required to train neural nets dramatically. So what this means is, you want to get into AI, you are going to be messing with this. You're going to have to know what this is. This is like, when was this announced? 25th of September. This is like cutting edge, bleeding edge, real world. What are they doing with it? Well, what they're doing is, in this article, they are explaining how to represent full floating point 32-bit in 8 bits. So now you have this massive reduction of complexity in the computational training for your neural net. That's huge, folks. You know, Bitcoin is warming up the planet, you know, where it takes so much energy to mine Bitcoin that the return is, you know, kind of nil. But this is explaining kind of what they're doing and how they're, and they go into the details of it in the article, which I'm not going to get into, but basically they take the numbers between 1, the square root of 1, the square root of -1. And they take those numbers and they use those as the floating points for numbers that are high, say like 100.123.123.123. Instead of calculating it out to 32 bits, they represent it in 8 bits using this posit idea. And you're all going, I don't get it. It's okay. What I'm pointing out to is it's still ones and zeros. That's what I'm saying. Okay, it's still ones and zeros. And this is something that I find interesting, because this sort of thing is, this is what's going to make AI close to human-like. Okay, how many believe AI will become Skynet and they'll kill us? Okay, all right. There's nothing wrong with that assumption. That's a legitimate assumption. But let me explain to you why it's not going to happen for real in at least my lifetime, maybe yours. I don't know.
Am I imagining something, or was there computers that they started to talk to each other, so they had to turn them off? They started talking in a language.
Yeah, they created their own language and nobody knew what was going on. No, that's a true thing. Facebook was doing that. Yeah, but the thing is, what were they communicating? We don't have any idea. Could have been nonsense. We had no way of inspecting it. And that's a problem with AI, is that you create a neural net and it creates these wonderful pictures, but you can't drill down inside of a neural net to figure out how it made its decision. If I can ask you, why did you choose computer science? You generally have an idea of why you are here. Okay. AI doesn't really know how to do that. That's a very active area of research. Is it how do you find out how AI got that answer? Because if I take the model you created and the model you created, and I give it the same exact training data, I'm going to get different answers. Okay. And we don't know why that is yet. So figure that out and you'll make your gazillions of dollars. This is why we won't have computers that reason like human, because we are bound in something called von Neumann architecture. Okay. And von Neumann is all ones and zeros moving around between registers up and down. We will be able to create AI that is very, very good in particular problem domains, like maybe driving a car or medical diagnosis or image recognition. But you can't take that AI model from driving a car to doing a surgery. It won't work because they are bound by the von Neumann architecture, which is bound by discrete structures, ones and zeros. Now, the big question is, what happens when we move to quantum and we have 1, 0, and all the stuff in between? Then AI will approach what we call human consciousness, because you're on a completely different platform. Okay. You're not bound by ones and zeros. You're bound by probabilities. So if we don't know how AI works now in the world of ones and zeros, how are we going to understand AI when it's in the world of quantum? Fascinating stuff, folks. This is the kind of future that's rolling in on you. You call a bank, you get a chat window that's over the phone, and they talk you through things trying to solve all your problems, when you really want to just hit zero and talk to a human, right? Well, that kind of thing is going to get closer and closer to human-like behavior, because my son-in-law happens to work for a financial firm and he spends a lot of time on the phone helping people. All of those conversations he's had since he's been hired are being recorded and analyzed and shoved into AI models. So eventually you'll be calling and you'll be falling into an AI tree for your questions. What will happen to his job? You betcha. Okay. And this is kind of what we're seeing in the world of automation, is what can we automate so we can save labor? You know, Robo Burger, McDonald's has had the robot flipping hamburger for decades, but now they're working on a robot that does French fries, specifically French fries. Why? That's where most fast food accidents happen, because of the hot grease. So I'm going to have a robot running hot grease. So what's going to happen is you won't have people working the fries, so to speak, at McDonald's, but you'll need a technician to fix that robot. But how many robots can one technician work on? That depends on how good the robots are. I used to work on copiers, printers. In the early days, you could only handle about 5 or 6 in your territory because they were so crappy. And then as time went on, the territories got bigger and bigger and bigger because the machines were better and better and better. So, I'm glad I'm out of that business. There's still a need for copy repairmen, but for the most part now, the copy machines are so smart, when they go bad, they send a message through the internet to the tech saying, come fix me. And the people who own the copier don't even know that their machine needs help. IBM's been doing that on their big servers for years. Okay. So what we're going to do is play with some of this stuff. And what I want to do is show you where you can actually get some demos of where this stuff is. Let me bring up I had a text editor window. Here we go. Let's go to this website here. And I will put this, it's called Circuitverse. Okay. So it's circuitverse.org. Okay. And you can actually build your own circuit. Okay. So you can say, you can learn it here, you can play with it, you can have sorts of things in here. And some of these links I'm going to give you today actually let you build your own CPU like that guy did on Minor website. Okay. This is a job. This is low level computer engineering type work. Okay. This is you're designing CPUs. Okay. So let's look at the simulator here, and we'll look at one of those. It's going to give me so here we go. So I can set this up to give you a test and all sorts of things. Okay. So let's look at a project. So I can save new ones, a circuit, new circuit. Now, let me explain a little bit about this Verilog. When you design your circuit, you can actually save this circuit and you can turn it into something called an HDL, which is a hardware description language that actually takes ones and zeros in your drawing and turns it into, shall we say, Boolean algebra / code that you can actually burn a chip. So you can actually create chips. There was a thing at the RISC-V conference that showed this high schooler. He said, yeah, I created my own RISC-V computer. High school. How did he do it? Well, dad was a programmer and mom was an electrical engineer. So he had a lot of help. But nevertheless, high school. I think that's pretty cool. Okay, so write these websites down. I'm going to bring them up to show you these different things. Okay. And then there's another one called Simulator IO. Okay. Now you're going to say, I'm not going to need this in a real job. Define real job. Okay. All right. Let's say I want to learn how to be an auto mechanic. Okay. And I have never used a wrench or a screwdriver or a pair of pliers in my life. I don't even know how to hold them. I don't even know righty tighty, lefty loosey. How long is it going to take me to become a good auto mechanic? There's a lot of good stuff I got to learn before I get there, right? This stuff is in that category. Okay. This is the foundational pieces that weave together computer science so you can become effective. Okay. You may not need it, but you kind of need to know that where your limits are. Okay. So there's number 2. Yep. And what's happening is a lot of the tools are abstracting away complexity. And here's the next big problem. Let me go through these and show you these first. These are all different websites that do kind of, in essence, the same thing. And then we'll talk about the differences of them. This one's called sciencedemos.org.uk, and it's under the physics section here. and you can do these logic gate simulators. And there's some presets here. Okay. Flip flop. What's a flip flop? Flip flop is so cool. That's how we do memory. All our memory in our computers are nothing more than flip flops. We hit a button and it holds a 1, hit another button, holds a 0. That flip flops hold memory. Okay. And then we have one more. There are more out there, but I wanted to start with these so you could kind of play with them and see the differences and see where they're the same. Whoops. Let's see. CEU GitHub.io. Well, I guess that one. Oh, maybe I need to. Yeah, that's what I needed. So that one, you'd have to actually fully qualified name here. That one is CEU computing.github.io/logicsim2. And this does the same thing. It's all in animation. Okay. Now you can use any one of these and play around with it. And you can use these kind of as an out of ZY books type of scenario to see what you've got. Now, if I was at the level of teacher that you would probably get in a 4-year school for this same class, is I would give you a Boolean expression and you write the circuit for it. That would be homework 1. The other homework would be, I give you a logic circuit and you write the Boolean expression. Okay. But I'm not going to do that. Okay. But I'm telling you, that's what I'm leaving out. Okay. That's a pretty big piece of the puzzle. Okay. All right. So let's take a look at some of these presets on this one. This is an addition. It's a 4-bit adder. So you can actually play with this. This is on sciencedemos.org.uk and /logicgates PHP. And I'll put these in the Canvas shell where it says phillipsd.org. I'll add those links in there so you can actually see them. But this is actually showing you how it works. If you get familiar enough with playing with this, just play with it. Learn by experimentation. I'm a big believer in that. The best way to learn is stub your toes. Okay. Here, doesn't work. It doesn't work. It's not going to hurt anything. So you can play with these and see how it works, and you can see the logic diagrams. Now, this is a certain kind of circuit. Got the line on it. But what is that? You don't remember, that's fine. Exclusive OR, and the little circles mean not, which means it flips. No, these are connections. Never mind, those are connections. So these are our AND circuit. Here's our OR circuit, and then there's some exclusive ORs, and these are going to help us use 1s and 0s and add to get an answer with a carry bit. Okay. Now, as you work through the ZY book stuff, there's going to be a lot of stuff you don't quite understand, but most of the stuff that's in the ZY books is readings and participation. Okay. You're reading it, you're answering questions, you're getting this vague idea of what it is, but you're not going to mastery, folks. This class is not going to get you to mastery. Ain't going to happen. Okay. There's just too much covered. That won't stop you from learning it on your own. Okay. And you're saying, well, I got what I needed out of the class. That's fine. Okay. All right. Now, let me shrink this back down. Here's circuit verse, where you can actually new circuit, and you can each one of these have different ways you can play with it. But let's play with this This one is out of Sweden, and this actually shows you, here's one, diode matrix, a traffic light. Here's how a traffic light works. Back when I was in school, when I took a digital electronics class, we actually did this. But there was way more connections than that because the logic wasn't there. This was like, geez, 80, 79, 80, long time ago. Okay. All right. So here's a clock and we have the counters and it says, okay, here's our decoder. Well, what's a decoder do? Well, what's some of these symbols? Now, I'm not going to teach you how to read schematics. That's computer electronics. But there's a few things you should know in the world of schematics is when we look at these samples, let's go back to, let's just go back one here, click. And let's go to a half adder, okay? All right, what a half adder does, it takes and only adds, let's say I'm going to add 4 numbers or 4 digits here, okay? It only adds up to the point where there's no carry. So they call it a half adder because there's no carry, okay? Well, if your logic, you need to have a carry to make it work out. And that's what a full adder does, is it deals with this carry bit. And what do you do with the carry bit? How do you represent it? When you run out of registers and ones and zeros, how do you represent it? Okay, that's what a full adder does. So it explains it, okay? The latches, which actually hold state, okay? So these are all fun things to look at. And here's a full-on circuit for a true 4-bit CPU. I think that's cool. You can play with this and you can throw inputs in and see what happens. So this will actually do simple addition and subtraction. Okay. Now, you don't have to design it. You can just poke ones and zeros on it and see what happens. Experiment with it. Okay. And this one, there's a ripple counter for, yeah, that's fine. Okay, so each one of these we can play with. Now, let's go back to ZY books. Now, in our ZY books, they're asking you to basically follow these instructions. And it says, okay, replace the AND gate with an OR gate. Okay, so we take this, we say delete, and we want to put that over here. And we make the connections, right? And so on and so forth, okay? That's pretty easy. We're not dealing with too much complexity here, okay? Now, where are we going with all this? We're going to get through some of the basics in the ZY books here, where we get through timing. Like this is the kind of thing that read, get an understanding of it, maybe answer the questions, and you're going to forget it anyway. Okay. I know that. Okay. But I'm also telling you that this is going to help you in the acquisition of learning a new tool so you can become that good auto mechanic. Okay. Maybe this is the torque wrench. Okay. All right. So that's kind of where we're going at this point. And then as we move down more through the logic, I'll talk about this one next week. We will spend the majority of the class 8, 9, 10, and 11. Okay. This is where I'm going to teach you how to take your C source code. We'll be working in C. We could use C++, but our C code is going to be simple enough it won't be hard for you. If you know any curly brace language, it's going to be pretty straightforward. We're going to take the C language. We're going to compile it to assembler. We're going to look at it. We're going to take that same C language and compile it for the debugger symbols. And we're going to watch the debuggers. And we're going to see what happens at 1s and 0 level. All this stuff in ZYBucks up to that point is to get you there. Debugger and the skill of the debugger is a big deal. Okay, that's truly something that will help you the rest of your career, is knowing how to debug your code. That point, here's the problem we're having in the world of software today. I'm a high paid full stack web dev. Okay. I come in and I build your app. Okay. And it's running on Node.js and it's perfect. It's everything you want. It works on mobile. It does this. I take my money and I leave. You come along and you get a job taking care of this app. You don't know anything about it. And the boss says, make it work. That's real world, folks. That's reality. You're going to be dealing with this stuff and you don't know how to even start. What do you do? Call? Hey, Mr. Boss, how do I do this? He's not going to know either. So how do you start figuring things out? Troubleshooting Basics, Chapter 1. You start seeing what happens when you press a button. You start using things like the web browser dev tools to see what's going on in the browser. Then you can use the debugger in Node.js and see what's actually happening and saying, hey, oh, look here, we've got this library that's corrupted. Just change the library. This is where most jobs are, is that you get given something and something breaks and you have to figure out how to fix that. And that break almost always is in some sort of log files. Okay. Always look at your log files first. Okay. That's step one, troubleshooting. It's kind of like a roadmap, especially if this whole thing is set up on Amazon. Let's say it's an Amazon instance and the high paid consultant is gone. You have to take care of it. Of course, you know, the high paid consultant can come back for a nice large fee to fix this problem. And this does happen in the world of consulting, is that people will write stuff that's so complex that they have to call the consultant back. Job security, they call it. You don't want a job like that because somebody's going to figure out what you're doing and you're going to be set free to pursue other alternatives. Okay. But this is reality. And then understanding how these layers work. What are the application programming interfaces that are being called? When are they being called? What data is going to and from them? Almost everything you do in school, you create from scratch. You write code to do X, Y, and Z. And it's usually pretty simple stuff. Okay. Write a compiler, do this, do that. But when you get out there, it's a whole different world. Now, if you look on YouTube and say, things I wish I knew before I was a computer science major or whatever, they all say the same thing. I needed to code more. Anything, everything. Code more. Scratch your own itch. Make up things. Add a function. Do things that are not in the homework. That's how you learn this stuff. Okay. All right. So back to where we are today is we are in. So we'll be doing these. Okay. So let's look at our timing diagrams here and I'll explain a little bit about timing. Okay. Now, this is the timing diagrams. Your machine has a clock speed, right? How many know what the clock speed of their CPU is? Okay, a couple of you probably build your machines from scratch and you know that they're going faster or slower. Well, anybody know what the original IBM PC was? 4.7 megahertz. We could do a DIR and watch it go click, click, click. Actually see it go. Now you are so fast, you can't see anything. Okay. Why is that timing diagram and that clock speed important? Well, let's use this example of RAM. Let's say I store a 1 and I've got some gate and I'm storing a 1. How long does that 1 live in a chip, basically? Forever? Hour? Something to know. In the world of RAM, we have to have a clock so we can push all the 1s and 0s through our logic at the right time. In the world of RAM, we have a clock that refreshes the memory at a certain rate. You've got your PC, you've got your RAM, you've got this giant Word document open, and all of a sudden you lose power and the machine just turns off immediately. What happens to that Word document? Disappears, right? You might be able to restore some of it, but why did that happen? Memory, if not refreshed, will return to 0. This is a timing diagram. This is part of the clock cycles and the things that happen. We send out, okay, we change a 1 and 0 in RAM, but we need to keep this timing and we refresh it with the clock speed. So my 1 stay 1 and my 0 stay 0 until I take what's in RAM and write it to disk. And then it will be there for my consumption later. Now there is a new part of RAM that's coming that they've been working on for several years now, but it's actually a type of RAM that's getting faster and faster, but it's maintained state. So imagine no disk drive, kind of like an MV2 drive or an MV4 drive, NVM drive, but faster and more dense. You can instantly save everything. And how would you change your programming talent to work with something that is permanent? What changes would you have to make down at this low level when you put a 1 in and you don't have to worry about timing? It kind of changes the model a little bit. So, I keep up on a lot of this stuff just because I find it interesting and it gives me more stories to tell, for you guys. Open your eyes to see what's available out there. It's like, there's a big world, okay? But this timing diagram, what they're doing with this one is that these are my inputs based on timing. So a 0 is this, a 1 is that. Well, what is this and that? Depends. It could be a negative signal or a positive signal, but generally speaking, it's 0 voltage and 5 volts. That's a close enough to throw on the wall, okay? The idea is that there's a difference in voltage. Now, as chips have gotten better and faster and smaller, that difference in voltage gets smaller and smaller, 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 okay? So maintaining that refresh cycle have to go faster and faster and faster because there's less and less change and these chips are getting closer and closer and closer together, okay? Yeah, the line diagrams, okay? And So it says, okay, complete the timing diagram. So what would you have to do here to complete the timing? So this is more experiential. You're playing with it, and all these little pieces are beginning to build up. You're building up these little tiny pieces, and those circuit simulators allow you to take, hey, I want to take two OR chips and turn them into an XOR chip. What do I need to do? How do I take one little picture out of that XOR stuff? Here's a nice integrated circuit with 5 NANDs in it. How do I take those 5 NANDs and do something with it? Well, you've just programmed a 7400 IC chip, because that's kind of what's in there, 5 NAND gates, okay? And we do not get into programming peripherals. When I took assembler here back in the dark ages, we actually had, 16-bit CPUs, and we had a light gun, and we would interface low-level assembler to the light gun to use feedback from the screen to say what pixel you were on. We don't do that anymore. It's that kind of thing. But it's more about stepper motors and robotics now. So you get your Raspberry Pi, use the GPIO, use a stepper motor to go forward, X number of steps, turn left, X number of steps, and have it make a big circle. Or put your pin on your little robot and have it draw a pattern on the floor. Or have it, download the libraries so you can have eyeballs in your little robot so it can measure distance. And then you can have it follow motion and torment your cat. Okay. That's where a lot of this stuff is going. So that's kind of where we're doing this. Okay. So what I want you to do now is play with these while we have some time. Just play with these. Okay. Now, let me take them and put them in our website so you can actually use them. All right. And then I'll put it there. So let's do it this way. Now it's going to be not very pretty. Let's see, where should I put it? Okay, I'll put it right there. All right. Sure how that's going to work. All right, so now if you go into Canvas and click on Philips the things, labs and links, these right here, okay? You can just highlight those. And I'll make the hyperlinks work. But I want you to just take some time. We got 20, 30 minutes. Just play, okay? You've got some uninterrupted time, no distractions. Just tinker with these logic gates and put them together, see what you can come up with. Okay. So basically bring this up, right click, and then just go to, and then you can play with it. Okay. And you've got questions, ask. Okay. And I'll fix the links so they actually work. Oh, I do want to mention that. The circuit verse. Let's see where we go. Here we go. Circuit verse. Scroll down. This is called the simplest possible computer. This is a full-on computer that will actually do a few instructions. Okay. And it actually shows you what you can do. Okay. And it's a full-on computer. It's a great way to learn logic diagrams because you're actually, it's pretty small. Let me make that a little bigger. Okay. It's actually using chips like this chip right here. You can buy it. And you can actually make this computer on a breadboard. Okay. And it's showing you how it works. When I saw this, I said, this would have made learning this stuff so much easier when you get to play with it. Okay. Because remember, I want you to be familiar and kind of a vague idea of what logic and Boolean algebra and all that is. We're going to get into the details and we're going to be writing assembler, probably not this week, but next week. Okay. The fun thing is you can take the output of that and burn a chip. That's just way too cool. Create your next hack 5 tool. There's also software you can actually buy that does this sort of thing for you. And then it goes like into Verilog, which is the hardware description language, and burn your own chip for, say, car fuel automation or something. I'll be here from about 11 on tomorrow. So if you want to come in and work on a server, play around with one, ask more questions about things that are not related to the class or computer science in general, stop on by. Okay. There. It's a little better now. Looks oh, that's too big. Let me fix that one. Want to learn how to create a web page and put it in your living room? That's the, I was going to save till the end of the class, but I don't want the recording to go on for 30 minutes. So I want to do a very quick thing of why you should join the ACM. The ACM is the Association of Computing Machinery. Okay. And it's a member organization. And for students, all you need is your .edu, and it's $19 a year. What do you get? More than you could possibly explore for the rest of your lifetime. They have just added Pluralsight to the ACM. Every professional software person I know, their company buys them a yearly subscription to Pluralsight for $4.95 to $6.95 per year, and you can get it for 19 bucks. What is it? What do you want to learn? I've got a job interview on AngularJS. You now have curated content that gives you the actual skills for AngularJS. Nothing else. It assumes you know how to code, okay, at a fairly decent level, okay? You can also say, hey, I want to get better at JavaScript, and say JavaScript intermediate or beginning, and refresh your memory and work your way down. You want to learn about DevOps, you want to learn about security. This is all industry slanted learning. You're learning specific tool that you need in industry to solve problems like we talked about. Here's a Node.js app. What's wrong? First of all, what's Node.js? How do I manage Node.js? What packages are they using? So this is golden, folks. This is really golden. I wish I had it when I was where you are. This saved me a lot of heartburn and late nights. Okay, now I'll stop the recording. Stop share. Stop recording.